different ways. I would just pick which one makes more sense to you. So graphing quadratic functions. So the graph of a quadratic function, I've already mentioned, but it's called a parabola. Okay, and that's this U-shaped graph. The axis of symmetry is just this invisible line that divides it into two separate halves because these halves it's symmetric. So if and knowing that it's symmetric actually can help us graph quite a bit. We have what's called a vertex, which is the point either at the very bottom or the very top. So that's helpful. And then notice the parabola is going to face up if that leading coefficient, which is the number in front of the x squared, if it's positive, it's going to face up. If it's negative, it's going to face down. So that can kind of help you just check if you're on the right path for graphing. So I've got some instructions here in the box for how to graph. There's different options like I've shown you before. I think that the easiest way is to find the vertex and to pick some values on either side of x. And actually with the graphing software we have, if you were able to just put this in the graphing software, you could also graph it that way. But I'm going to show you how to do it by hand. So the formula for finding the vertex, it's actually right up here, is negative b over 2a. That's the x coordinate of the vertex, and then you have to plug that into the equation to find the y value of the vertex. So I'm going to go ahead and do that. So we have this function here, and our a value is 1, our b value is negative 6, and our c value is 5. So I'm going to find the vertex by doing negative b over 2a, so negative 6 over 2 times 1, or 6 over 2, and I get 3. And then I'm going to plug that in. So I'm going to do 3 squared minus 6 times 3 plus 5. And when I do that, I get negative 4. And so the vertex at this point is 3, negative 4. And so I plot that 3, negative 4, 1, 2, 3, 4, and that's my vertex. And then I can look at the graph. The leading coefficient is positive, so I know it's going to face up, but I don't know how wide or how skinny it is. So what I could do is I could just plug in an x value. So maybe I plug in, I could plug in, I don't know, maybe 0, because that's an easy one to plug in. So if I plug in 0, so if I plug in x equals 0, I get 0 squared minus 6 times 0 minus 5. So I get 0 minus 5, so I end up getting negative 5. So that means the point 0, negative 5 is on the graph. So I'm going to go ahead. Oh, and you know what? I did that wrong because I'm looking at it. If it was 0, negative 5, it would be down here, and I just said that this is a face-up graph, so I must have done something wrong. So let me go ahead and look. You know what? I wrote down minus 5, and this should be a plus. There you go. So just knowing the general shape of the graph, see how that caused me to fix my mistake there, because I knew that it should be facing up. So 0, it should be 0, positive 5. I'd like to say that I did that on purpose to show you, but I did not. So 0, 1, 2, 3, 4, 5 is right there. Now the cool thing about parabolas is they're symmetric. So if you go over 2 or over 1, 2, 3, up 1, you can go from the vertex, you can go 1, 2, 3, up 1 on the right side without doing any other work. So that gives you a good general idea of how to graph. Now there's other methods, like I said, you could do more points if you wanted to, but that is you know, I think that that's a great starting off point just for this class. And then don't forget too, you can always use the graphing software Desmos to double check your work. So let's try some story problems with some quadratics. So this first one, we've got a model of percentage of the population where X is the number of years after 1900. So pay attention there. When you've got problems like that, it just makes it a little trickier. So we're going to say X, we're just going to highlight that so that way we are aware of it. So part A, when did the percentage reach its low point? Anytime you have a quadratic, remember that's a parabola, either facing up or facing down. In this case, the A is positive, so it's going to be facing up. If we want to know the low point, that's going to be talking about the vertex. So this question is basically just saying, find the vertex. So we're going to do x equals negative b over 2a. That's the formula for the x value of the vertex. So in this equation, my A is that 0.0033. This is B, this is C. So I'm going to do negative 0.420. Notice negative is in the formula. So if B is negative, you've got to account for both of those negatives there. Divided by 2 times A, 0.0033. And when I do that, I get 0.420 divided by 0.0066, and I end up getting 64. So that means the vertex is 64, comma, we don't know. But it's just asking when, and remember the x value, that's years. So I don't even need to find y. That would be the population, or the percentage of the population. I don't even need that because it doesn't ask for it in this question. So I'm going to say 64 years after 1990. And so if I do the math on that, or not 1990, 1900, so that would be 1964 would be my answer for that one. So the next one, when was the percentage? What was the percentage? So what was the percentage? We're looking for y in 2012. So we have to figure out, well, how many years after 1990 or 1900 is that? So from 1900 to 2000 would be 100 years, and then in 2012 that'd be another 12. So this would be like x equals 112. So all this is saying is plug 2000, find p of 112, find p of 112. So we're going to take our equation and plug in 112. And then if we plug it in and we do all the math on that, we end up getting about 13.9%. And I didn't tell you how to round in this, so I'm just going to approximate it like that. Just pay attention when you're doing your homework. You should have rounding directions there. And then for C, if the model accurately predicts future trends, what will the percentage be in 2020? So you'd have to figure out, well, what is the x there? So that would be x equals 120, because that's 120 years after 1900. So you do the same thing as we did earlier. We just plug in 120. So if you plug in 120 to the equation, you end up getting about 16.6. So 16.6% about there. Okay, so we've got one more story problem for quadratics, and there's one like this in the homework, so I definitely want to get to this one. So projectile motion function. So we've got this is a general function that you can use anytime you've got projectile motion, which just means that something is being thrown up in the air, or thrown in general. And I just want to point out, so this v, we call it v naught or v sub 0. This is initial velocity. You're going to need to come back to this later because in your homework you're going to also use this. And this h sub 0, that's your initial height. So as you read the problem, I want you to jot those down because we're going to need to plug those in. So if a bowling ball is launched upward from the top of a 230-foot building, so if you have this building, and this building, we'll say, is 230 feet tall, and you've got a bowling ball, it's going to be thrown up. Okay, if it's thrown up, it eventually will come down. So you can see that that curve looks like part of a parabola. It has initial velocity, so I'm going to write v sub 0 as 60 feet per second. Find the maximum height and how long it takes to reach the ground. So we weren't specifically given the initial height, which we need, at least it didn't say it in those words, this is the initial height, but we were given the height, and the height is 230 feet. That is the initial height of the bowling ball. So h sub 0 is 230 feet. So I'm going to go ahead and write this function, but instead of v sub 0, I'm going to write 60, and instead of h sub 0, I'm going to write 230. So just to be clear, I put the 60 and the 230 in myself. Those were given in the problem. The rest of the numbers are given to you. So the first question it says is find the maximum height. Anytime you want to find the maximum height of a parabola, that's going to correspond to the vertex. So let's go ahead and find the vertex. So to find the vertex, we're going to do negative b over 2a. So in this case, my b is 60, so negative 60 over 2, my a is negative 16. So I'm going to go ahead and calculate that, and I end up getting 1.875. Now this is going to be my x value of the vertex. So the vertex is a coordinate pair, so 1.875, that's the x value, and it says that the input in this case is going to would be time, because if the velocity is 50 feet per second, this would be seconds. So it means that after 1.875 seconds, that bowling ball is at the highest point in the air. But notice it didn't ask the time for the maximum height, it asked the maximum height. So we actually have to plug that into the equation to find the max height. So I'm going to take negative 16 and I'm going to plug in 1.875 to the equation. And I end up getting 286.25. So max height is 286.25, and we know it's feet because the velocity was 60 feet per second, and that occurs at 1.875 seconds, but they didn't ask for that, so we just stopped there. And so that's the first part. And then the second part, how long does it take to reach the ground? Well, when it reaches the ground here, the height is going to be 0. So basically that's like saying when is height, or in this case it would be h of t, equal to 0. So we're going to plug 0 in for h of t and we're going to solve. So I'm going to plug 0 equals negative 16t squared plus 60t plus 230. And this is where you have a couple of options. You could factor, you could use the quadratic formula, or you could go ahead and use your graph. So one way is just to plug it in. So I'm going to just type in 0 equals negative 16. Now in this case I'm going to use x just because that's the input variable that the system uses. It'll give you the exact same graph as putting a t there. And so we can see, I'm just going to zoom out here. Whoops, actually maybe what I can do is maybe I should zoom in. There we go. Okay, and so again, we're looking for when the height is 0. So the height is 0. There's two options here. So the height is 0. We've got two options, negative 2.355 and 6.105. You have to choose. Now keep in mind that the x value represents seconds, time, so it doesn't make sense to have a negative time. So I'm actually just going to ignore that one. And my answer is going to be 6.105 seconds. So 6.105 seconds. And it is totally fine to use the graph like that. And if you use the quadratic formula, you would end up doing the work and you would end up getting those two answers. And the other one was negative 2 point something. And you would just cross off that negative one because it just doesn't make any sense given that time can't be negative. So I hope that makes sense, but definitely let me know if you have any questions. All right, so let's go ahead and talk about exponential functions. So we're going to do some quick graphing and then we're going to do some story problems. So exponential functions are functions that look like, I'll just give you a general shape. So they look like either like this or like this. And you may have heard the term exponential growth or exponential decay, and that's just referring to, when something grows really rapidly or when something shrinks or decays really rapidly. And so the form of this equation is this right here. So C is just a number, and A is a number, and the exponent is x. So there's a couple things about this graph. When the a value, we call that the base, when it's greater than 1, the function's increasing. So for example, if you add the function f of x equals 3 to the x, that's going to be an exponential growth. If the a value is less than 1, so if it's like f of x equals 0.5 to the x, then it's going to be exponential decay. It's going to be decreasing. And then it does have a horizontal asymptote, which just means that it never touches the x-axis. It gets really, really close to the x-axis, but it doesn't ever touch. So how do we graph? Very similar to the other ones. We can just pick some x values, plug them in, and then find y. And then you have your graphing software, the Desmos, to double check. So let's do this first one. So we've got f of x equals 2 to the x, and I'm just going to pick some x values here. So I'm going to pick -2, 0, 2. So if I plug in -2, I get 2 to the -2 power. And you could certainly use a calculator for that if you need to. This means 1 over 2 squared. When you have a negative exponent, it just tells you to put in the denominator, which is 1/4. So the point here, if we look at the coordinate pair, so this is your y value is 1/4, but the coordinate pair is -2, 1/4. So that's your first point. So -2, and I'm just going to go up just a tiny bit, 1/4. And then if I plug in 0, 2 to the 0 power, anything to the 0 power is just 1. So the point there is 0, 1. So 0, 1. Oh, and it looks like that one disappeared. There we go. And then if I plug in 2, 2 to the 2 power, you get 4. So 2, 4. So if you want, you can keep going, but your graph is just going to look like this. And then remember, there's that horizontal asymptote there, which means that this graph gets really close to the x-axis, but it doesn't actually touch. And then the second one, notice that there's a fraction here, so that's going to be a decay. So I'm going to go ahead and pick some x values. And I'm just choosing, I'm going to pick the same ones, -2, 0, 2. Those aren't, the best x values to pick. I'm just picking them, and you can choose to pick more if it makes the graph more clear to you. So for this one, I've got 1/2 to the -2 power, and you could certainly use a calculator if you need to. That's going to be 4. And so that gives you the point -2, 4. 1, 2, 3, 4. And let me show you, and I'm going to show you real quick on the TI-30 how to put that in the calculator. You could use your fraction button, and then you could do, so 1/2 come out of your fraction, and then just use the exponent key, and then you're going to type in -2, and that gives you your answer of 4. And then 1/2 to the 0 power is just 1, so that gives you the point 0, 1. And then 1/2 to the second power is 1/4. And again, you could use your calculator if you need to, or actually write that out, 1/2 times 1/2, and multiply fractions that way. So this is a big module. So I think that if computing this is not your strength, it's totally fine to use a calculator. So I'm just going to plot those points. So 0, 1. And then 2, 1/4. And then, if you want to do more, then that's great. It gives you an idea, but I think this is okay too. And this is totally adequate in terms of being able to do your homework. So let's just go ahead. We've got 2 more problems here. I know this is a long video, but I want to get these done too. So we've got 2 story problems. And this first one, it gives us this function to model population. And notice you've got this a sub 0 here. It's the population at time 0, which just basically means initial population, like when we're starting this, when we're starting this investigation. So the problem says the population in 2007 reached 2 million for the first time. So let's let that be our initial population. So we'll say 2 million is our initial population, and that's starting at 2007. So that's where we're starting this function. It says use the model to predict the population in 2027. So if x equals 0 corresponds to 2007, then we need to figure out what x corresponds to 2027. And since it's 20 years later, then that would be x equals 20. So basically, all we have to do is plug 20 in for t. So we're going to do 2 million times 1.04 to the 20th power. And then I'll show you how to enter that into the calculator. So we're going to do 2 million. So we got 6 zeros, 4, 5, 6, parentheses, 1 point, whoops, missed that decimal there, 0.04. And then we're going to do exponent key, and then we've got the 20. And then there's your answer. So I'm just going to write down on my notes. So it looks like we've got 4,382,246 people. And then always ask yourself, does it make sense? This A value, it's bigger than 1, so there should be growth. So it makes sense to me that we started with a population of 2 million and then it grew quite a bit in 20 years, which is what you would expect. And then the last one, we're going to look at the compounding interest formula, because that's also an exponential formula because we have a variable in the exponent. So this says if $10,000 is invested, so that's our principal. So remember back from module 2, so $10,000 is our principal. It's invested in a rate of 8%. So if the rate is 8%, then that corresponds to 0.08 as a decimal, because we're moving our decimal 2 spots to the left. And then it's compounded quarterly, so that means our n is 4. And you can go check out the module 2 notes if you want to refer, if that doesn't ring a bell. And then we want to know the value of the investment after 40 years. So that would mean t equals 40. So remember, t is always in years. So I'm just going to plug all of those numbers in. So 10,000 for p, 1 plus my rate over my n times t, and then you can go ahead and just plug that into the calculator. And so remember, you can plug that in exactly how it looks. So if you've got the TI 30 or 34, you can plug it in. You can also do this on the graphing calculator. So I'm going to do parentheses 1 plus, I'm going to use the fraction key, 0.08 divided by 4, and then parentheses raised to the 4 times 40 power. And then you're left with $237,699. And if we round to cents, where it's going to be 7 cents, which is kind of crazy to think that's $10,000. You put in 10,000 and you get, over 200,000. So the power of compound interest. So let me just go ahead and write that final answer. So $237,699.07. Holy moly. Wow. All right, so we are done. I know that is a long module, so thanks for hanging in with me. Please let me know if you have any questions. I'm here to help.